Now that we know Green's theorem is true, let's work out a couple examples using this surprising fact. So the thing about Green's theorem is it can let you turn line integrals into double integrals or double integrals into line integrals. And it's always just up to you to keep in mind that it is switching between the two is a possibility for any given calculation. When it is appropriate to do so just depends on what you're calculating. So here's an example. Let's calculate the circulation of this vector field around this unit circle. Now, if you think about what we would have to do to calculate this, right? We'd have to parameterize the unit circle, which is going to give us some sines and cosines, and then plug that mess into F, and then work out a dot product. And it seems like it might be a mess. It might be bad. Okay, but what we can do instead is, right? Green's theorem gives us another option. Because we're integrating around a unit circle and we're going counterclockwise, Green's theorem gives us the option of switching to a double integral, right? So we could do the double integral over the unit disk, which is the interior of the unit circle. We can integrate over the unit disk the curl of F. And this might be simpler, right? So let's see what that would look like. The curl of F is going to be, let's see, partial n partial x, so 3x squared, minus partial m partial y, so plus x squared dA. Okay, so how would we integrate this? Oh, so actually this is going to be integral of 4x squared. Yes? Yes. Okay. So which would you rather integrate? Some messy line integral with tons of sines and cosines lying around, or 4x squared over this disk? I mean, I would rather integrate 4x squared over this disk personally. So let's do it that way, right? So over this disk. Doing it this way doesn't totally get us away from having to deal with sines and cosines, because I think the easiest way to compute this integral over this disk would be to use polar coordinates, which is what we'll do. But this integrand is just so much simpler than the integrands coming from this line integral would be, right? So this still is going to be easier. So to do this double integral, we need to, let's see, for the unit disk, remember dA is r d theta. Right, our origin is here, so theta is going to go from 0 to 2 pi. R, we need to go from 0 out to the edge of the disk, so that's from 0 to 1. And then 4 times x squared. X is r cosine theta in polar coordinates. So when we square that, we get r squared cosine squared theta. And this integral is eminently doable, right? This one is pretty straightforward. Our bounds are all constants, and our integrand is a product of a function of r and a function of theta, so we can separate this integral into the, move that 4 all the way outside, integral from 0 to 2 pi of cosine squared theta d theta, and then times our r integral, which is the integral from 0 to 1 of, looks like we have r cubed total, dr. Okay, so 4 times, for this theta integral, we do still need to use one of our trig identities, but at least we only need to use it once, right? If we had done the original line integral, we would have had to use trig identities multiple times, and that makes a real mess. Okay, so this is much better, even though we do still need to use trig identities once. All right, so now we're set up to integrate. We get 4 times, so times that 1/2, and then our antiderivative for the theta integral is theta plus 1/2 sine 2 theta from theta equals 0 to 2 pi times, and then this r integral is going to give us 1 over 4r to the 4th from 0 to 1. Collecting all these constants, it looks like we have a total of 1/2. Okay, and then for our theta integral, we're going to get a 2 pi plus 0 minus, and then when we plug in zeros, we get zeros. Okay, times, and then for our r integral, 1 to the 4th is 1, minus 0 to the 4th is 0. So this whole thing turns into, looks like it's pi. Okay, so you can see that that Green's theorem gives us the flexibility to choose which kind of integral we would rather do, a double integral or a line integral. And in many cases, if the region isn't too complicated, switching to the double integral is easier. It's not always easier, but sometimes it's easier anyway. Let's look at one more example. So let's find the circulation of this vector field over the boundary of the annulus, which has r coordinates from 0 to 2. So this is, an annulus is a ring shape, so like this. So we're integrating over, over the boundary of this region, which is going to be right on the outside. To keep the region on our left, we have to be going counterclockwise. And on the inside portion of this region, to keep the region on our left, we have to be going clockwise, right? Okay. Now, again, in this particular example, we could just calculate the circulation by doing two line integrals, the one around the outside and then the one around the inside. We could do that, but we should also think about what the double integral would look like. So we could integrate, we could do this line integral, dr, or we could do the double integral over the region of the curl of r. So let's see what the curl of f. So let's see what the curl of this vector field looks like. So let's see, partial n partial y is, no, I need partial n partial x. So I have to do the quotient rule on n. So it's going to be 1 times x squared plus y squared minus x times the derivative of the bottom with respect to x is going to be 2x. That's a multiplication, not a minus right there. All over x squared plus y squared squared. So this is going to be, let's see, x squared minus 2x squared is minus x squared, and then y squared all over x squared plus y squared squared. Okay, so there's partial n partial x. If we work out partial m partial y, right, the other part of the curl, right, we're going to differentiate this one with respect to y, so we get a minus, and then so derivative of the numerator is 1 times x squared plus y squared minus derivative of the denominator with minus y times derivative of the denominator with respect to y is 2y. This is starting to look familiar. All over x squared plus y squared squared. Okay, so this is minus. Looking at the x's, we get an x squared. Looking at the y's, we get a minus y squared over x squared plus y squared squared. Okay, but now we can use this minus sign to turn that subtraction around. So we get y squared minus x squared over x squared plus y squared squared. All right, so that's partial m partial y, but the curl is the difference of these two. So when we subtract these two, we just get 0. So for this case, I would definitely rather do the double integral curl because it's going to turn out to be 0, right? All right, so because the curl of this vector field was 0, the double integral is definitely easier. But notice that this actually tells us something a little bit surprising, which is that the integral of this vector field dot dr around just one of these circles, say the unit circle, right, which is the inside circle, that has to be equal to the integral around the circle of radius 2, f dot dr. Right? And this is because we know that if you do the integral around the outside counterclockwise plus the integral around the inside clockwise, those add up to 0, because that gives us this double integral, which we saw as 0. But if you do them in the same direction, that means instead of canceling, they're exact, right? Since they cancel, that means they're the same but opposite signs. So if we do them in the same direction, that means they have to be exactly the same. So these two are exactly the same. And in fact, this shows that the integral around a circle of any radius will always be this exact same value. And in fact, I think we actually computed this value in class at one point. It's 2 pi or something like that. Okay, so for vector fields whose curl is 0, knowing that the curl is 0 tells you interesting things about line integrals, because right, if you have the integral around two curves, if those two curves make a region, then you know the integral around those two curves is equal to each other, because for exactly this region. Green's theorem tells us interesting things about line integrals in general, but especially line integrals for vector fields whose curl is 0.